Okay, so what we found is that by normalizing, we can find this normalization constant a. So this, what we did the integral. You have to look up the integral basically of e to the minus x squared over from minus infinity to infinity, e to the minus x squared, but the or e to the minus ax squared. But then we arrive at this solution, and if we then solve that, okay, so I've just rewritten that, and if we solve that for a, we get the fourth root of m omega over pi h bar. Now, some of you may wonder how we could. I said that a in general can be complex, and so how we can all of a sudden arrive with something which is clearly real. There's nothing here which all these numbers are real and positive, okay, and so we clearly have a real value for a, for the normalization constant. Well, the thing is that you can choose one of the constants to be if a were complex, then the magnitude wouldn't change, but just the phase would change. And since all the solutions are related to each other by these raising and lowering operators, that would change the phase for all of them. That is, it would change the how much the normalization coefficients for all the wave functions, all the solutions would be mixed. There would be some imaginary parts mixed in that would all be related to this particular solution. So we are free to choose that phase, okay, in the complex phase to be so that we get a completely real answer for one of the wave functions, but then we're no longer able to adjust anymore. So we can make that choice for one of the solutions, and then all the other solutions are dictated by that one. Okay, so we've just chosen this. In this case, for this particular solution, we've chosen a to be real, and when you plug in this normalization constant now right here, then you get the full ground state wave function as written. Okay. Now that gives us the ground state wave function, but we still need to find the ground state energy associated with that wave function. Okay, so to find the energy E naught associated with the ground state wave function psi naught, then we just use the time independent Schrodinger equation, which, if you remember, is written the Hamiltonian operator on psi naught needs to be equal to the energy of the ground state times psi naught right back. Okay. And so we choose to use a particular form of one of these two forms of the Hamiltonian operator, okay? And so we use the one that has the raising operator first, okay? A plus A minus, and that gives us plus 1/2 h bar psi naught. Again, that has to equal to E naught times psi naught. And if you remember, from up here, the lowering operator operating on the ground state wave function gives you 0 because it can't be lowered any further. Okay, and so if we rewrite this as h bar omega a plus a minus times psi naught plus 1/2 h bar omega times psi naught is equal to E naught psi naught. Then what we notice is that what we have right here is the lowering operator operating on psi naught, and this is equal to 0. So this whole term is equal to 0, and what we find is that E naught is equal to 1/2 h bar omega. So the ground state energy for the harmonic oscillator potential is equal to 1/2 h bar omega, where, if you remember, omega is related to the spring constant, okay, the stiffness of the harmonic oscillator potential, and the mass, okay. Omega is equal to root k over m, where k is again the spring constant. And so we have found the ground state energy for the wave for the harmonic oscillator potential.